Section: Introduction. In this section, we delve into the introduction of our study, which focuses on the performance of large language models, LLMs, in complex tasks. Despite their impressive abilities in generating language, understanding context, and reasoning, LLMs often fall short when tackling intricate problems. To address this, recent research has turned to ensemble methods and frameworks that allow multiple LLM agents to work together, enhancing the overall performance. For example, the LLM debate method uses several agents to debate and refine the final answer for arithmetic tasks, showing better results than a single agent approach. Similarly, the COT-SC method generates multiple thought chains and selects the most consistent one, improving reasoning by leveraging more thought chains than the traditional single-chain approach. Our observations from these studies suggest that combining multiple agents can, to some extent, boost performance in certain problems. This is evidenced by preliminary findings showing that increasing the number of debating agents in LLM debate leads to higher accuracy. Additionally, employing more chains of thought pipelines, as seen in a sample and marginalize decoding procedure, also results in performance gains. This leads us to believe that simply scaling up the number of LLM agents could enhance performance. However, the detailed exploration of this scaling effect has not been the primary focus of previous works, leaving a gap in our understanding. To fill this gap, we embark on the first comprehensive study of the scaling properties of LLM agents. We propose a straightforward sampling and voting method that involves generating multiple outputs from a single or multiple LLM agents and then using majority voting to decide the final result. This method, inspired by COT-SC, simplifies the process without relying on complex thought chain designs. Our experiments, conducted across various LLM sizes and datasets, reveal that increasing the number of agents generally improves performance across a broad spectrum of tasks. Remarkably, an ensemble of smaller LLMs can match or even outperform larger models, a finding we will expand upon in later sections. By integrating our method with other existing approaches, we further enhance performance, demonstrating that our simple technique can compete with more complex methods without additional prompt design or collaboration frameworks. Our results also suggest a link between the effectiveness of our method and the difficulty of the tasks, prompting us to investigate how problem difficulty influences our method's success. We categorize difficulty into 3 dimensions: inherent difficulty, reasoning step length, and the prior probability of the correct answer. Through experimentation, we observe how adjustments in these dimensions affect performance, allowing us to identify optimization strategies that capitalize on the more agents approach. Our contributions are significant. We present a systematic study on the scaling effect of LLM agents, showing that performance improves with more agents through a simple sampling and voting method. We demonstrate compatibility with existing methods, enhancing their potential and achieving further improvements. Our analysis of varying problem difficulties helps us understand the underlying reasons for our method's effectiveness, leading to the development of further optimization strategies. In related work, we categorize existing studies into 3 areas: LLM self-ensemble, heterogeneous LLM ensemble, and multiple LLM agents collaboration. Our method stands out by being effective in both reasoning and generation tasks, compatible with a wide range of methods, and not requiring additional training data, unlike many supervised learning approaches. We also explore combining our method with selected representative methods for even greater performance enhancements. Section Summary. In this section, we explore the use of multiple large language model, LLM, agents to enhance the performance of LLMs in tasks requiring reasoning and generation. By employing a simple sampling and voting method, we demonstrate that increasing the ensemble size of LLM agents can generally improve performance across a wide range of tasks. Our study reveals that a brute force ensemble of smaller LLMs can achieve comparable or superior performance to larger LLMs, without the need for complex collaboration frameworks or handcrafted prompt designs. Section: Method. In this section, we explain our approach, which is carried out in 2 main steps: sampling and voting. We start by giving an overview of our method, which is illustrated in a figure in the paper. During the sampling phase, we consider a task query, symbolized by X, and a large language model, LLM, denoted as cal-M. Here, our goal is to create n samples by either directly querying the LLM n times, where each sample is represented as S equals cal-M, X, or by combining it with other methods, noted as f_cal-M, and executing this n times to get each sample, denoted as S equals f_cal-M, X. By the end of this phase, we have a set of samples, S equals S_1, S_2, S_n. Moving on to the voting phase, our aim is to come up with a final answer, A. To do this, we use a majority voting system to consolidate the sample set, S, into A. This involves calculating the total similarity for each sample compared to the others, which is represented as V, S_I, equals sum_J equals 1, JNEQI, caret N, sim, S_I, S_J. For tasks that require generating new content, like writing code, we use the blue score to measure similarity. On the other hand, for tasks with fixed answers, like multiple choice questions, we measure similarity by how often the same answers occur. The sample with the highest total similarity is chosen as the final answer, represented as A equals operator name *arg max _S_I in S. V S_I. We describe the entire sampling and voting process in an algorithm provided in the paper. Next, we discuss our experimental setup, which is separate from our evaluations. This setup is designed to cover a range of scenarios or tasks to compare with related works, to test the backbone language models we use, and to see how well our method works with other methods. For our experiments, we focus on several tasks: arithmetic reasoning, where we use the GSM-8K and the more challenging math dataset; general reasoning, selecting the MMLU and a dataset from a chess state tracking task; code generation, where we use the human eval dataset and calculate the blue score among all pairs of generated candidate answers to select the final output. Regarding the language models, we test our method using different scales of models from the Llama 2 and GPT series, including 2 versions of Llama 2 Chat optimized for conversational use cases, and GPT 3.5 Turbo and GPT-4. To check the compatibility of our method, we integrate it with various typical methods from 2 categories: prompt engineering and multiple LLM agents collaboration. We evaluate several prompt engineering methods and generate multiple samples using methods like LLM debate and self-reflection, employing majority voting to determine the final answer. We average the results over 10 independent runs, scaling up the ensemble size to 40 for maximum gains, except when using the debate method, where we limit the size to 10 due to computational overhead. Our experimental results show that our method generally improves performance across all tasks and LLMs by increasing the ensemble size. For example, in arithmetic reasoning tasks, we see accuracy gains ranging from 12% to 24% on the GSM-8K and from 6% to 10% on the math dataset. In general reasoning and code generation tasks, we also observe significant accuracy gains. Interestingly, our method allows a smaller LLM to outperform a larger one by simply scaling up the ensemble size, with the enhanced Llama 2-13B model achieving higher accuracy than the Llama 2-70B model in some cases. Section Summary. In this section, we introduce our method, which involves a 2-phase process: sampling and voting. During the sampling phase, we generate multiple samples by querying a language model multiple times and integrate with other methods if needed. In the subsequent voting phase, we use majority voting to select the final answer based on cumulative similarity metrics, such as blue score for open-ended tasks and occurrence frequency for close-ended tasks. Section: Compatibility. In this section, we explore how our method can be combined with other techniques to enhance performance across various large language models, LLMs, and tasks. Our findings show that when our approach is integrated with others, there's a noticeable improvement in results. Specifically, in arithmetic reasoning tasks, we see our method boosting performance by 10% to 21% on the GSM-8K dataset and by 1% to 15% on the math dataset. For general reasoning tasks, merging our method with others typically results in performance increases of 1% to 13% for the chess task and 1% to 11% for the MMLU task. In the realm of code generation, combining our approach with different methods leads to improvements ranging from 2% to 7%. However, we observed two exceptions when our method was used alongside the Llama 2 to 13B and Llama 2 to 70B models, where the performance actually dropped. This decline is mainly due to the noise created when referencing the answers from multiple agents, which disrupts the logic of the generated code. Moving on to the effectiveness of our method, we discovered that it generally outperforms other methods when used alone, except in the chess task with the Llama 2 to 13B and Llama 2 to 70B models. Additionally, we calculated the average performance ranking of each enhanced method across various tasks, and our method emerged as the top performer without requiring extra prompts or complex collaboration frameworks among LLMs. Regarding robustness, we conducted ablation studies to assess how changes in certain hyperparameters affect overall performance. These experiments were carried out using the GPT 3.5 Turbo model over an average of 20 runs. Our findings indicate that increasing the ensemble size consistently improves LLM performance across different tasks, despite variations in these hyperparameters. To understand the performance gains better, we analyzed how the effectiveness of our method varies with the difficulty of the task. We chose two datasets, GSM-8K and Math, with increasing difficulty levels to calculate the relative performance gain. This gain is measured by the difference in performance, accuracy, between using our method and a single LLM query. Our analysis revealed that the relative performance gain is more significant with increasing task difficulty. For instance, within the same task, the smaller model, Llama 2 to 13B, showed gains ranging from 28% to 200%, but only 8% to 16% over GPT 3.5 Turbo. Moreover, the more challenging math task yielded gains of 34% to 200%, compared to only 16% to 69% on the easier GSM-8K task. To delve deeper into this, we categorized the difficulty of a given task into three dimensions: the inherent difficulty of the task, the number of steps required to solve it, and the prior probability of the correct answer. We then designed experiments to isolate and analyze each dimension. For example, we created a mathematical task where the variables are randomly chosen integers within a specified range, representing the inherent difficulty. The number of terms in the summation indicates the number of steps needed to solve the problem, and the result space is divided into intervals of equal probability, representing the prior probability of the correct answer. Through these experiments, using GPT 3.5 Turbo as a case study, we measured the relative performance gains by comparing the maximum accuracy achieved by our method, sampling 40 times, against the accuracy of a single LLM query, sampled once, averaged over 10 runs. Section Summary. In this section, we integrate our method with other methods to enhance performance across various LLMs and tasks, resulting in performance gains ranging from 1% to 21% in arithmetic reasoning tasks, 1% to 13% in general reasoning tasks, and 2% to 7% in code generation tasks. However, integration with Llama 2 to 13B and Llama 2 to 70B models led to performance degradation due to noise generated by referencing answers from other agents, disrupting code logic coherence. Our method generally outperforms other methods in standalone cases, except in specific instances like the chess task using Llama 2 to 13B and Llama 2 to 70B. Additionally, our method achieves the highest average ranking across different LLMs and tasks without requiring additional prompts or complex collaboration frameworks. Ablation studies show that scaling up ensemble size consistently improves LLM performance across tasks, despite variations in hyperparameters. The efficacy of our method varies with task difficulty, with more substantial relative performance gains observed in more challenging tasks. For instance, smaller models like Llama 2 to 13B show gains ranging from 28% to 200% in difficult tasks compared to 8% to 16% over GPT 3.5 Turbo, emphasizing the impact of task complexity on performance improvements. By categorizing task difficulty into dimensions like inherent task difficulty, number of steps required, and prior probability of correct answers, we conduct experiments to isolate and analyze each dimension's influence on performance gains. Section: Inherent difficulty. In this section, we delve into the concept of inherent difficulty and its impact on performance gains. We start by adjusting the inherent difficulty level, denoted as I, from 10 to 400, while keeping other variables constant. Our findings, illustrated in the left figure, reveal an interesting pattern. As we increase I, performance gains initially rise, reaching their peak at I equals 100 and I equals 200. This suggests that our method is particularly effective when the difficulty level is elevated. However, when I is pushed to 400, we observe a decline in gains, indicating a possible overload on the model's reasoning capabilities, which in turn leads to diminishing returns under extreme task difficulty. Moving on to the number of steps involved in a task, we explore how performance gains are influenced. By varying the number of steps, S, from 1 to 8 and keeping other variables steady, we notice a direct correlation between the number of steps and performance gains, as shown in the middle figure. Interestingly, when both I and K are increased, indicating a higher level of difficulty, the performance gains are even more pronounced, ranging from 4% to 18% over a baseline to as much as 16% to 48% for more challenging settings. We further refine our analysis by introducing a technique called sampling and voting at each step of a task. Despite each step having the same level of inherent difficulty, errors tend to accumulate, leading to a decrease in accuracy as the number of steps increases. However, by applying our sampling and voting method stepwise, we effectively mitigate this decrease in performance. Building on this, we propose a stepwise sampling and voting approach that prompts the language model to break down the task into multiple steps. Through iterative rounds, we select an unprocessed step, apply sampling and voting to determine its outcome, and then update the task based on this result. This process is repeated until all steps are processed. Our experiments, with S equals 8 and K equals 4, and tuning I from 100 to 400, demonstrate that stepwise sampling and voting significantly outperforms simple sampling and voting, with gains increasing alongside inherent difficulty. Lastly, we examine the role of prior probability in performance. By adjusting the parameter K, which inversely affects prior probability, we observe that an increase in prior probability leads to improved performance. This is visually supported by the right figure across various configurations. To capitalize on this insight, we introduce a hierarchical sampling and voting method that leverages the relationship between performance and prior probability. By decomposing tasks into high-probability subtasks and addressing them hierarchically, we can enhance performance. This approach also allows for cost savings by employing simpler models for easier subtasks. In our experiments, we use GPT 3.5 Turbo in a homogeneous setup and a combination of GPT 3.5 Turbo and GPT-4 in a heterogeneous setup. The results confirm that employing a hierarchical method, whether in a homogeneous or heterogeneous model combination, significantly boosts performance, demonstrating the effectiveness of our approach in a cost-effective manner.